This is Physics 2212, Lab 5, Magnetic Molasses. In this lab report, I will first introduce the experiment and explain the empirical procedure and the coding component. I will then follow with the results, discussion, and the conclusion. The purpose of this lab was to compare the experimental time taken for a bar magnet to fall through a tube of aluminum foil with the simulated time calculated by a computational model. The fundamental principles of this lab include Faraday's law, Ohm's law, the magnetic field of a dipole, the magnetic force on a wire loop, the force of gravity, and the position and velocity update formulas. These equations are provided on the slide for your reference, and all of them will be used in the computational model to predict the time taken for the bar magnet to fall through the foil tube. A preview of the results: the average experimental time was 1.184 seconds, and the predicted time was 1.389 seconds. The values are very close, but the model overpredicts the time the bar magnet spends inside the tube. For the experiment, the system is the bar magnet and the surroundings are the roll of aluminum foil, the earth, and everything else. The length of the tube, the width, the inner radius, and the outer radius are also all provided on the slide, as well as the mass of the magnet and the magnetic dipole moment that was determined in Lab 3. As for the key assumptions of the experiment, we assume negligible air resistance and that the primary factor affecting the magnet's motion is the induced magnetic field. The procedure is very simple. While recording, drop the bar magnet through the tube of aluminum foil. Repeat this 5 times. Scrub through the video to find the timestamps for the magnet entry and exit, and calculate the average time spent by the magnet inside the tube. For the checkpoints, why can't we use a ferrous tube? The bar magnet will be attracted to the size of the tube and interfere with its falling motion. And for the second one, what happens to the magnet and how does this compare to a magnet falling in free space? The magnet falls slowly through the tube, noticeably slower than if dropped in free space like onto a table. For the coding aspect, the constants are μ0 over 4 pi, the resistivity, and g. The images on these slides represent the calculation steps performed in the code. First, the magnetic field of the dipole is defined, and then the d phi over dt. The ring current is found from Ohm's law, V is equal to IR, and then the magnetic force is found using the equation in the introduction. The net force takes into account the magnetic and gravitational force, and finally, velocity and position update formulas are used to iterate the predicted position of the magnet in the tube to find the time it spends inside the tube. As for the result of the model, the predicted time is 1.389 seconds, while the actual time was 1.184 seconds. For the interpreting the simulation questions, by applying Lenz's law, the red color must be counterclockwise and the blue clockwise, as this combination would oppose the magnet's motion, which is what we observed. The dynamics of the system would not be changed if the magnet is flipped, because it would still slow down, but the currents would be the opposite of this experiment. To increase accuracy, a greater number of rings to create the tube, as well as accounting for air resistance felt by the magnet. And as for the shape of the graph, the forces are unbalanced in the first 0.1 seconds, and then they are balanced for about 1.1 seconds and unbalanced again in the last 0.1 seconds. This is likely due to the start and end of the tube's effect on the magnet. Lastly, for the discussion and conclusion, possible sources of error include some contact between the magnet and the tube as it fell, introducing forces not accounted for in the simulation, for example, friction, air resistance. The foil tube may not have been the same radius throughout its length, and there may have been measurement inconsistency due to human error. For the additional questions, a nearly zero resistivity would imply a very small resistance and thus a very large current. This would increase the magnetic force and make the magnet fall very slowly through the tube. Holes or slots cut into the tube would disrupt the induced current and decrease it, reducing the magnetic force on the magnet and letting it fall much quicker through the tube. In conclusion, the actual time was 1.184 seconds, while the predicted time was 1.389 seconds. These are very close values and indicate that the model is successful in predicting the motion of the magnet to a good extent. Thank you.